as your second eigenvalue. So the simple way which you could have solved this, you could have just jumped straight without even wasting time. I believe whatever I just explained now is what you actually did in Maths 1. So the simplest way to solve this, you could have just said, since we have our matrix A, which is, we had 2 1, we had 2 1 1 2, we have our matrix A, this is our matrix A. Well, to determine our eigenvalue, how are we going to determine our eigenvalue? You can just jump straight using your absolute values. It's going to be 2 minus lambda 1 1 2 minus lambda, which is equals to 0, and then after you apply our determinant to get the values of lambda 1 and also to get the value of lambda 2, because basically this was just a definition to show you how you can actually apply this formula. But if you're given a matrix like this and you're required to determine your eigenvalues, you can just subtract lambda from your diagonals. Let's say maybe you have a matrix 3 by 3, a 3 by 3 matrix. For example, this is A is equals to 1 2 4 7 3 2 1 1 1. Let's say you have this type of matrix, and then you're actually required to determine your eigenvalue. To determine your eigenvalue, this is simple. You just jump straight into what? Into solving this question. How? Your absolute 1 minus lambda 2 4 7 3 minus lambda 2 1 1 1 minus lambda, which is equals to what? Is equals to 0. If you pay attention to this problem which I'm solving now, you can see that all your diagonals, we subtract lambda from all your diagonals. If you check here, it's lambda lambda lambda, and then you use your method of determinant. Use your determinant to actually get your values. So from the previous session, from the previous slide, you can see we have solved this and we got lambda 1 as 3 and lambda 2 as 1. This is what we call our eigenvalues. Now let's actually move to our eigenvectors. To get our eigenvectors, every eigenvalue has its own corresponding eigenvector. Okay, let me just write this down. Every eigenvalue consists of its own eigenvector. So every eigenvalue consists of its own eigenvector. You have seen from the previous slide that we had matrix A, which is equals to what? Is 2 1 1 2, ne? And we got our first eigenvector as 3 and our second eigenvector as what? As 1, ne? So for each and every eigenvector, we're going to have our unique for each and every eigenvalue, which is lambda 1 is equals to 3 and lambda 2 is equals to 1. We're going to have our own unique eigenvector. So let's start when lambda is equals to, with lambda is equals to 1. Obviously we're going to do the simple one. It's going to be 1. When lambda is equals to 1, let me just do this, erase this. I need a space here. When lambda is equals to 1, remember when you determine your eigenvalues, you said 2 minus lambda and then 1 and then 2 minus lambda, ne? So you're going to substitute the value of 1 where you see lambda, and then you're going to end up with 2 minus lambda is going to be 2 minus lambda, or lambda is 1, is going to be 2, and then we're going to have 2 minus lambda is 2 minus 1, means we're going to be left with 1. And then here we have 1, our 1 here, and then 2 minus lambda, it means we'll be left with 1, and then we'll multiply by our magnitude k1, k2, which is equals to what? 0, 0. So we need to get our vector. We're actually trying to get our eigenvector here. So how will we get our eigenvectors? To get our eigenvectors, we're going to say k1 plus k2 is equals to 0, and then k1 is equals to negative k2. And then from this point, we're going to let, if we let k2 to be equals to 1, this implies that k1 is going to be equals to negative 1. So we have our k1, which is equals to negative 1, and our k2, which is equal to 1. How are we going to write our eigenvector? To represent this using an eigenvector, we're going to have our capital letter K, which is equals to what? K1 and K2, which can be written as our K1 is what? Is minus 1, and our K2 is what? Is 1. So basically your eigenvector is what? Is K, which is equals to minus 1 and 1. And then this is how you get your eigenvector using your eigenvalues. So if we had to solve for lambda is equals to 3, we're still going to follow the same process. It means that we're going to substitute our 3 where we got what? Lambda minus, where is it? Here we're going to substitute 3 here for lambda, and then we get our matrix and we write it in this form of a vector, and then we get our k1, k2, and then we represent it in this format. So I'm gonna stop here to cut the video short and to avoid confusion.